This video is on applying Newton's second law of motion to cars and banked roads in circular motion. Question 1. Use Newton's second law of motion to find an equation for the speed of a car moving in circular motion on a horizontal road with surface friction. So, circle the object, label the forces, put an x and y axis. So what's happening is this is a car and it's moving in a horizontal circle. So if there is circular motion, then there must be a net force towards the center of the circle. So that's the centripetal force. If there's no force of friction, then the car will be moving in a straight line forever. So we need a force towards the center. So look at the forces on the y-axis. Sigma F sub y equals ma sub y equals plus force normal minus force of gravity. So that's here. Now, let's take a look at the horizontal forces. Sigma F sub x equals ma sub x equals mv squared over r equals force of friction, which is here. Force of friction is mu force normal, and now we're going to solve for force normal in yellow, so we could substitute it here. And then we could just solve for v. So that's the equation for a car moving in a horizontal circle with a radius r and force of friction mu. Question 2. Use Newton's second law of motion to obtain an equation for the speed of a car moving at an angle theta to the horizontal and circular motion on a banked or angled road with no friction. So try to imagine what's happening. This car is moving in a circle, but it's not a horizontal surface. It's been raised up in angle theta, so it looks like a cone. So circle the object, label the forces, put an x and y axis. So remember, it says this road has no friction. So the only forces we have is force normal up, 90 degrees from the surface, and force gravity down. So step 1, sigma f sub y equals ma sub y. The forces in the y direction is force normal cosine theta minus force of gravity. And this object is not jumping up and down, so acceleration on the y-axis is 0. So when yellow, we have an equation for the vertical motion. Step 2, we're going to use sigma f sub x equals ma sub x equals mv squared over r. What forces do we have on the x-axis? Well, if you look at the image, it's only force normal sine theta. We could substitute for force normal to go here, and we could solve for v. So v equals root gr tangent theta. Remember, question 1 had force of friction, question 2 has no force of friction. Question 1 has theta equals 0, question 2 has a non-zero theta. So in question 2, you could see as r and theta increases, then v also increases. Question 3. Use Newton's second law of motion to obtain an equation for the speed of a slow-moving car. So this object is moving in a circle on a banked road, but it's moving slow. Why did we underline slow-moving car? Because it gives us the direction of the force of friction. And this object has a surface friction with the road. So step 1, circle the object. Step 2, label the forces. Step 3, put an x and y axis. Step 4, use the equation. So in question 2, there was no force of friction. In question 3, there is a force of friction of a slow-moving car. So the reason why the force of friction is to the right is because the friction is going to stop this car from going down. Because it's slow-moving, it's going to want to fall down. So step 1, use sigma f sub y equals ma sub y. A sub y is 0. What is sigma f sub y? It's plus force normal cosine theta minus force of friction sine theta minus force of gravity equals 0 newtons. We know force of friction is equal to mu force normal, and now we're just going to solve for force normal. Step 2, sigma f sub x equals ma sub x. So that's going to be force normal sine theta minus force of friction cosine theta equals mv squared over r. In circular motion, A is equal to v squared over r. We know force of friction is equal to mu force normal. We're going to factor out the force normal. Then we're going to substitute force normal, which we found from step 1. Here. And now we could just use algebra to solve for V. What we could do is you could let theta equal 0 to see if we get the same solution as question 1. But in question 1, force of friction doesn't point to the right, it points to the left. What we could also do is let mu equals 0 to see if we get the same solution as in question 2. Because if mu equals 0, one term in the numerator and one term in the denominator go away. Question 4. Use Newton's second law of motion to obtain an equation for the speed of a fast-moving car moving at an angle theta to the horizontal in circular motion on a banked or angled road with surface friction. So remember, question 3, the car was slow-moving, so force of friction was up the incline. In question 4, the car is fast-moving, so the force of friction is down the incline towards the center of the cone because the force of friction is going to stop the car from moving up. In question 3, the force of friction was going to stop the car from moving down. So remember, question 3, it was a slow-moving car. In question 4, it was a fast-moving car. The only difference is the direction of force of friction. So step 1, remember, circle the object. Step 2, label the forces. Step 3, put an x and y axis. Step 4, use the equation. So sigma f sub y equals ma sub y. A sub y is equal to 0. So now we have force normal cosine theta minus force of friction sine theta because force of friction points down minus force of gravity is 0. So we get this for force normal. Step 2, sigma f sub x equals ma sub x. A is equal to v squared over r. Sigma f sub x is force normal sine theta plus force of friction cosine theta. We know force of friction is mu Fn. There's an Fn here and an Fn here, so factor that force normal out. Then we could substitute for force normal in yellow. And finally we get this equation here. So let's see if our equation for question number 4 equals our equation for question number 2 if we let mu equals 0. And let's see if our equation for question 4 equals our equation for question number 1 if we let theta equals 0.